today we will discuss central limit theorem. Okay. So, with today we will be done with your today is the last lecture as far as your syllabus is concerned. Okay. Again, the central limit theorem is not one theorem, it is a family of theorems of which we will do the most simple version for IID random variables. Just like law of large numbers is also valid for more general under more general assumptions of some weak correlations and so on, right. But we will do central limit theorem only for IID random variables. Okay. So, the central limit theorem, say at a very high level, the central limit theorem establishes the importance of the Gaussian distribution, all right. So, we know already that if you were to add any number of independent Gaussian random variables, you will get another Gaussian random variable, right. That is something we have already established, right. So, as long as they are independent, if you keep adding independent Gaussians, you get another Gaussian, right. So, this is another way of saying this is that the Gaussian distribution is stable. So, if you keep adding Gaussians, you will get another Gaussian. Similarly, you know the Cauchy distribution is stable, you keep adding Cauchy random variables, you get another Cauchy random variable, right. So, the central limit theorem goes ahead and says a little more about the Gaussian, particularly if you have finite variance random variables. Okay. If you keep adding a large number of finite variance random variables whose mean is 0, let us say 0 mean finite variance random variables, the sum looks like a Gaussian even if the original distribution is not a Gaussian, it can be anything with finite variance. Okay. So, that is roughly what the central limit theorem says, alright. So, your xi's, so if you are adding a number of xi's which are let us say independent and identically distributed, the distribution of xi's could be anything, okay, but with finite variance, okay. But the result of adding these independent identically distributed random variables looks more and more like a Gaussian when you add more and more terms, okay. So, this property is called, so this establishes, the central limit theorem establishes the Gaussian as an attracting distribution, not just a stable distribution, but an attracting distribution among finite variance random variables. Okay. So, Gaussian is not just stable, we already know it is a stable distribution because if you keep adding Gaussians you get a Gaussian. Now, we are saying that even if you are not adding Gaussians, as long as you add enough of them finite variance random variables, you will get something that looks like a Gaussian, which means it is also an attractor in this world of finite variance random variables. Okay. So, that is at a high level. So, one way to look at it is you know that, so Sn, so xi's are IID let us say. So, with mean expectation of x and variance sigma squared let us say, okay, or sigma x squared. Then you know Sn we defined as I equals 1 through n xi. So, from the law of large numbers we know that Sn over n goes to expectation of x, right, let us say in probability, right. Weak law says in probability, strong law says this is almost sure, right. So, another way of saying this is that if you take Sn which is the sum of the first n IID random variables and you subtract n times the mean, right, divided by n, you get something that goes to 0 in probability or almost surely, right. That is, so that you will admit, right. So, this is because of law of large numbers, right. I am just bringing this to this side. Okay. So, now, so if you look at this, so if you look at this term, right. So, this is Sn minus n times the expected value, right. This guy, so this result is saying that this difference is sublinear in n, right, as n becomes large. So, this ratio goes to 0, which means that fluctuation, right, Sn minus n times the mean, that fluctuation from n times the mean is sublinear in n, right, that much is clear from the law of large numbers. Agreed? Now, the central limit theorem gives a finer characterization of this fluctuation. Okay. In particular, it says that not only is this difference from Sn not only is this numerator is the difference sublinear in n, it further says that this difference is approximately like square root of n, okay, if you have a finite variance, alright. So, this is approximately like square root of n, alright, that is one of the things that CLT says. Even more remarkably, what it says is that this is like square root of n. So, if you were to have a square root of n in a denominator, you will have something that is like order 1, right, because this is like square root of n. So, if you divide the numerator by not by n, but by square root of n, you should have something that is like order n, order 1, right. Now, that order 1 term is a Gaussian fluctuation, that is what it says, okay, it is a now n01 fluctuation. Okay. So, I will just put that down. So, what the CLT says is in very loose terms, CLT says that Sn minus n times expectation of x is about as big as square root of n. So, this is obviously a very imprecise statement, but we are saying this is roughly a square root of n fluctuation for large n. Okay. And B says that the distribution of Sn minus n expectation of x divided by square root of n approaches the approaches the Gaussian distribution n 0 sigma square irrespective of the distribution of the x's. Okay. So, it says two things, as I said. So, this Sn minus n times square root n times expectation of x is approximately like square root of n. So, the sublinearity which we get from this law of large numbers, it is further qualified that this is not just sublinear, it is actually square root of n roughly for large n. And if you take Sn minus n expectation of x divided by square root of n, so that order 1 term you get is still a random variable, right, because these guys are random variables. So, that order 1 term you get by dividing by square root of n statistically looks like a Gaussian random variable. It in fact approaches the Gaussian distribution as n becomes large. okay, and this is true irrespective of the distribution of xi's. All we need from xi's is that it must have finite variance, okay. Any finite variance distribution is okay, anything you think of. So, things like Cauchy are not included because Cauchy does not have finite variance, it does not even have a mean, right. So, as long as you have finite variance, this will definitely attract to a Gaussian, okay. Is this clear? So, this is the IID version for the IID version of the CLT, right. It also holds under slightly, I mean there are some more general versions of CLT where you do not necessarily demand IID, right. You can relax, you can have some decaying correlations, or xi's can be differently distributed, but no one of them should dominate very strongly. In those circumstances you can get a CLT, but we will only bother about this IID version, okay. Theorem. Then so okay, un equal to blah 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 converges in distribution to a standard Gaussian random variable, okay. That is the central limit theorem. This is the precise statement. So, you have IID random variables with mean mu and variance sigma squared, and you have to assume that sigma squared is finite, okay. If sigma squared is finite, then this this object Sn minus n mu over square root of n, right. I have put the sigma down to get a standard Gaussian, right, otherwise you will get a Gaussian with variance sigma squared, okay. So, I have put this sigma down here in order to get a standard Gaussian limit, okay. So, then this sequence of random variables, let us call this un. So, these uns are centered by taking away the mean and scaled by sigma times square root of n, right. So, you have made un into a 0 mean a unit variance sequence, right. So, we are saying that this sequence of random variables converges in distribution to a standard Gaussian n01, okay. That is f. So, what is convergence and distribution? F un of x, when I am looking at the CDF, f un of x converges to, so limit n tending to infinity of the CDF must be equal to what? Error function of x, right. Error function or q, what did I use? ERF is what I used, right. So, this is what is this? Error function is integral minus infinity to x 1 over square root of 2 pi e power minus y square or something, y square over 2 dy. Okay. So, it says that the limit, if you take the CDF of this sequence, right, if un is a sequence of random variables whose CDF sequence of CDF converges to the CDF of the standard Gaussian. Okay. So, that is what the central limit theorem says. What the central limit theorem does not say is that the un will have a PDF converging to the bell curve, does not say that. Okay. That is a very big misconception. See what I mean. So, if you take these random variables un, right, first of all these uns need not have a density, right, because we have not assumed that these xi's have density, they need not be continuous, they can be whatever you want, right, any finite variance distribution will do, right. So, these xn's or these un need not have a density, right. So, in any case you do not, even if they have a density, it is not necessarily the case that you will have convergence of, at least the central limit theorem does not say that u1 will have a density that looks like the bell curve, that is not what the theorem says. Okay. This is a very big misconception, it only says convergence of CDFs, not PDFs, in fact the PDF may not exist. Okay. The convergence is to the error function, the CDF goes to the error function, it is not true that you approach a bell curve or un may not have a density and it need not have a density that goes to the bell curve. Okay. Is that clear? Any questions on the statement? So, this error, so this is a continuous limit, right. So, you do not have to have the problem of the convergence and distribution, you have the problem that you only need convergence at points of continuity, right, that problem does not arise here because this is such a nice function, it is a continuous function, right. Any questions? Okay, proof. Proof is actually very simple in the IID case. So, you let z I equal to, so I am just going to center these guys, I am going to center and scale the xi's. Okay. So, I am just going to take the mean away and scale by the standard deviation. So, I get these zi's will be 0, mean and unit variance. Okay. But these zi's need not be Gaussian, zi's are just the scaled version of xi's, right, they can be anything, they just have 0 mean and unit variance. And then you have un will be equal to sum over zi divided by square root of n, right. Great. So, let me consider C z I of t. Okay. So, these random variables z I have 0 mean and unit variance, therefore, the characteristic function must admit a Taylor expansion up to second order, right. So, it must, so this guy must look like what? So, you have a 1 plus I times 0 t, right, 0 is the mean, is not it. So, I times 0 times t, then plus I squared, so minus 1 times expectation of x squared, right, the second moment which is now equal to 1 times t squared over 2 factorial, right, plus there will be a little o term of t squared, is not it. fine, little o t square, okay, not big O, little o t square, okay, good. Now, so I want to eventually, so this is what I want, right, I want the characteristic function of C u n t. What I will eventually show is that C u n t as n tends to infinity converges to the Gaussian characteristic function, which we know is e power minus t squared over 2, right. So, so it is happy that I have a term like that now, right. So, I am going to try to calculate the central limit, so the sorry the characteristic function of u n. So, C u n of t, so now you have to help me. So, this is a, okay, this is square root of n here, but other than that this is just the nth power of C z I, right. So, if this is what this was not there, the characteristic function of the sum alone will be the nth power of the characteristic function of z I, because they are IID, correct. So, I think what turns up is that C u n t will be C z I of t over square root n to the nth, okay. I think this is what will come up, because there is a square root of n in the bottom, okay. I think this is fairly easy to verify. So, this will be equal to 1 minus t squared over 2 plus little o, well, okay, 2 t n power n, correct. So, I have to write, so I am taking the nth power of C z I of t over square root of n. So, wherever I have t, I write t over square root of n, right. So, I get t square over 2 n plus little o t square over n, fine, straightforward. So, now this converges to, so this is, so as n becomes large, so this is 2 n, okay. So, as n becomes large, this is little o t square over n, right. So, this will go to 0 very quickly, okay, and therefore, it will not play a role in the limit as n tends to infinity, this will just go to e power minus t square over 2, right. So, this goes to power minus t square over 2 for all t as n tends to infinity. Thus, u n converges in distribution. This is the characteristic function of a standard Gaussian, right. Right. So, it is a very short proof if you look at it, right. So, we have used characteristic function convergence to establish a very fundamental result in just 3 steps, okay. And this is a perfectly, I mean this is a perfectly rigorous proof, okay, I have not cut any corners here, right. The only thing you have to be slightly careful about is you have to show that this does not matter, you have to be a little careful in showing that is all, okay. So, this is a perfectly correct rigorous proof. There are many, see the many elementary textbooks on probability give many pseudo proofs, they try to manipulate the density and try to get e power minus x square by 2 for their density, right. Those proofs are not correct, because there is no proof, there is the convergence is not in the density, the convergence is in the characteristic function, therefore, the convergence is in distribution, okay. So, it is not at best these manipulations found in more elementary textbooks, they can serve as some intuition, serve to provide some intuition, but it is not a correct proof to use those elementary proofs, okay. This is the simplest and the most complete proof, is a complete proof of central limit theorem for the IID case. Any questions?